Okay, so for 27, I want to start by showing you some problems that can exist when you're trying to do a crossed aldol reaction. Let's say that you add some base to a mixture of two different ketones. Okay, well, this base can come and grab a hydrogen from here, right? Or it could grab a hydrogen from here. Or it could grab a hydrogen from here. Or it could grab a hydrogen from way over here. Every single one of those hydrogens that comes off would then attack another carbonyl. Okay, well, say that it was one of these. I'm just going to put an example down. Let's say that we ended up with this guy as one of the four different things that you could end up with, right? Now, who does he attack? Does he attack this? Or does he attack this other guy? Where's he going to go? You can't even tell, right? That's the problem with crossed aldol reactions and why it actually takes techniques in a lab to be able to control these types of reactions. We can use techniques in the lab in order to direct who ends up getting the hydrogen pulled off, just as we talked about last time as far as temperature of kinetic versus thermodynamic product, right? But we also can tell which one of these will react with the other one based on how we actually go through and perform this, okay? So we can end up getting lots of products that we really don't want. So let's look at some solutions that we can use in our design and of our lab experiment, okay? First thing that you can do is that you can restrict the number of hydrogens possible simply by having a reaction where there are no alpha hydrogens. Well, that makes it easy, right? This guy is the only one with the hydrogens, so you know they're coming off of there. Now, the only thing is that you must add this to the solution slowly that already contains this in our base. And the reason for that is that if you just put base in, it could react with itself or one of these, right? So you want this guy to react as soon as it hits, which means that you need this to be already in the solution, and then as soon as this hits the solution, bam, he gets his hydrogen removed, and bam, he reacts with excess of this that happens to be in there. So you've got to make sure that you're doing that in the right order. I hope that makes sense. Go back and review that. Go back and replay that if it doesn't, until it kind of sticks in your mind a little bit better. Because that's kind of hard to think through at first. The other option is that we can use LDA. We can use LDA because LDA is a very strong base and it will immediately remove the hydrogen in a direct approach. So here we have one component that contains an alpha hydrogen, and here we have another one, right? Well, if we want to do a crossed aldol between these two, what we do is we add the one that we want to remove the hydrogen from first. We then put in a strong base like LDA that immediately removes this hydrogen. You then add this guy in, completely opposite from the previous one. You add this one in slowly. As soon as he hits, bam, you want him to have plenty of this around to react with, giving you this product only. So yes, you have to make sure that you don't have too much LDA here because you don't want this to deprotonate as you're adding it to this guy. Okay. So I wrote out some guidelines here and you can look at that as well. Okay. Now, once you have your aldol, The other cool thing that it can do is that it can undergo what's known as a condensation reaction. And a condensation reaction does what you think of probably when you think of condensing, and that is it condenses water. You pull water out of the solution here. So what's happening is that once you make this guy, we're then removing OH and another H to make water, as well as this double bond right here. The cool thing is we could do this with either acid or base. However, you gotta add heat. You do have to add heat, excuse me. But in either case, you've already got base in here. So base is the way it goes most of the times, but you haven't seen this mechanism before. So this is known as the ECB mechanism. E1CB, excuse me. That base comes in and abstracts the alpha hydrogen. So a second alpha hydrogen. You have to have a second one in order for a condensation to be able to work. That's actually the reason why you can't do that here, because this is now a tertiary carbon, right? Or sorry, excuse me, it's a quaternary carbon. So no, you can't actually go ahead and do anything with that. But here, we're going to abstract our hydrogen, electrons go back, and we can end up making the enolate. As the enolate comes down, electrons go back here, that comes and grabs water, and that leaves. That's 4 windshield wipers all at the same time, just going like that, really, really fast, okay? So it's almost like it has to be in the right order, or the right configuration, electronically, for that to even occur. But you end up making a double bond right there. So you end up making a double bond where the new bond was made to begin with. We started with this guy, right? Where the second double bond oxygen would have been if I had drawn that out is where that double bond now is. Pretty cool. Now, do want to note that you could also do this anytime through acidic elimination. This is just like we've seen before with alcohols, right? So these electrons can come and grab that hydrogen, water leaves, water comes back and abstracts that hydrogen, and bam. So that's exactly what you saw with H2SO4 and alcohol before. Okay. In addition to having what's known as a Aldol reaction, there's also what we call a Claisen reaction. Well, Claisen reaction, the difference between it is we're actually doing this with now an ester instead. That's the pretty big difference. You are still removing this hydrogen. I'll show you that in just a second. So we do want to again use the same type of base here as what you would find on this side. So like if that's a ethyl group over here, you would use ethoxy, whatever it may be, because those will exchange in this process. But we're again connecting 2 of these guys, and essentially you're losing one of these. So let me show you how it goes together. This is the same as over here, right? Okay. Now, if you look at this one, he's the same as over here, but he's missing his methoxy. Okay. So let's look at that mechanism. Base comes and abstracts an alpha hydrogen, electrons go back. Once you have your carbanion ion, it will attract the second equivalent, electrons go up. Now, can you see I shifted this over, but here we go. This one has electrons up. He's right here. This methoxy is over here. As these electrons go down, this one leaves, and that's how this gets detached from the whole thing, giving you that as a product. Okay. And yes, you can do cross Claisens just like you can do crossed aldols. The same 2 types of techniques still apply. If you can find one with no alpha hydrogens, great. Then that would be like the strategy number 1. And you can even use LDA if you need to in the same format that we did in the previous, in the crossed aldols, excuse me. Okay, thank you very much. Almost done.